Hello, my name is Jared Skeens and welcome to the Zoom room. Today I'd like to cover Statistics 1, Distributions, Part 2, the Geometric Distribution. Last time we looked at the binomial distribution, which we saw as part of the formula had that N over R, that Pascal's notation, because the binomial distribution kind of plays off the algebraic concept of binomial expansion and uses Pascal's triangle or the coefficients of Pascal's triangle in determining part of the value for a specific value in the binomial distribution. So when we get to geometric distribution, it plays off of geometric series, which we looked at in the Peer 1 math video series. And so you're going to see a little bit of that flavor as we look at the concept. So first we want to look at, the thinking process, and then we'll get into a few of the examples. So this, by the way, is new material in the 2020 syllabus. So this is one of the basically the only new topic for the statistics book. Again, when you're looking at the distribution type questions, the very first thing you need to understand is whether your data is discrete or continuous. Both the binomial and geometric work with discrete data. Okay, remember, it's the normal distribution that's going to work with continuous data. So that's the first thing you want to figure out is it discrete or continuous? Then remember, with the binomial, there were 4 criteria, of which 3 of the 4 are the same with the geometric. So the one that's significantly different that we need to focus on, which is our second question after we determine discrete, is the number of trials. In the binomial distribution, there was a fixed number of trials. You had n trials. And so you would see n in the parameter, n and p in the parameters. Now, there is not going to be a fixed number of trials. You continue to have trials until you have the first success. Whereas in binomial, you had a set number of trials, and within that set, a certain number of successes and a certain number of failures. So in the geometric, you're going to continue your trials until you reach a success, which is going to happen on the rth term. So R is the subscript, the rth term within this sequence. So the criteria for geometric, it's not fixed number of trials. In other words, it can go on indefinitely. It can go on off towards infinity. So you will not have this many trials stated like you did with binomial. That is going to be your key point in distinguishing between the binomial distribution and geometric. As far as the rest of these, they will remain the same. The trials are still independent of each other. There's still 2 possible outcomes, success or failure. So the letter P will again represent success. The letter Q, which is 1 minus P, will represent failure. And your probability of success, P, is constant, again, demonstrating that you have independent events. So these are the criteria. The number 1 here is the one that you mentally want to focus on for determining geometric distribution. Now, let's explain or explore the concept of geometric distribution here really quickly, just so that you can kind of see where these formulas come from. With the binomial, there was a little bit more of a natural transition into the binomial formulas. For example, with mean in the binomial, it was x times p, meaning your x possible values times the probability. And it was a natural transition because the probability functioned like frequency. So the formula was very similar to your mean from a group data with frequency. It just changed frequency for probability. So as we change over to geometric, the formula is a little different because it comes from series instead of binomial expansion. So if we look at a probability distribution table where x is your possible values, in this case, x is going to represent the trials. So trial 1, trial 2, trial 3, and these trials go on indefinitely, okay? Then what is the probability that your random variable, whatever it is going to have a success on that particular trial, okay? So the big X, and it doesn't have to be X, it can be Y or Z, but I'm just using X in general for your variable. When will it have a success on that particular trial, okay? Or what is the probability of it having your first success on the first trial or second trial or whatever trial that goes? So if your success is on the first trial, well, then that means that's your success. You just have P. If your success is on the second trial, well, then that means you have one failure followed by a success. If your success is on the third trial, then it means you have two failures followed by a success. So as you can see, your number of trials minus 1 is the number of failures that you have before it's followed by a success. And this here, if we were to take this indefinite probability distribution table, it's indefinite because there's not a fixed number of trials. The number of trials can go on indefinitely. So it's different, whereas the binomial distribution table was fixed, only had certain values it could take. So as we change this into our formula for mean, the E of X, which we used in the binomial distribution table, the E of X then equals the X value times the probability. So 1 times P is P, 2 times PQ is 2PQ, 3 times PQ squared is 3P squared, and so on. And if we are to multiply both sides by Q, multiply this side by Q, multiply P times Q, we get PQ, which lines up with this as far as like terms. Multiply this one by PQ, and you get 2PQ squared, which lines up with this one, and so on. And then we subtract them, but we change our notation from the E of X notation to our mu notation, okay? So our mu, we saw that before as well. Mu equaled, that we had in the previous one, in P. We used mu equaled in P in the previous one. And when we subtract it, we get mu minus mu Q. Here, P minus 0 is P, 2PQ minus PQ is PQ, 3PQ squared minus 2PQ squared is P squared, and so on. These now all become coefficients of 1. And this follows a geometric sequence, where the first term is P and the ratio is Q. In other words, each term gets multiplied by Q as you go along. So this becomes actually a geometric series because you are adding the sequence as you go. So since this is a geometric series that is going on indefinitely, we can take the sum to infinity. So as we take the sum to infinity, our first term is P over 1 minus R. The ratio is Q. And Q is the same thing as 1 minus P. And when we subtract 1 minus 1, it cancels out. And minus a negative P becomes positive P. And P divided by P equals 1. Now this does two things for us. First of all, it demonstrates to us that the total of probabilities of the entire probability distribution table, even though it goes on indefinitely, still equals 1, which is important for the probability part. We need to make sure our total probability is 100%. So we've demonstrated that. It also allows us to replace the geometric series to infinity with the value of 1. So when we factor out the mu, which is our mean, the average, and divide the 1 minus q to the other side, and 1 minus q is the same thing as p. Q is 1 minus p, p is 1 minus q. They're like complementary of each other with respect to 1. And so 1 minus q is the same thing as p. This then provides us our evidence for where the mean comes from. So here we have the mean. Here we have the sum of the distribution equals 1. And I don't believe there's a variance to it because variance talks about the spread of the data, whereas in binomial, you have a fixed data set. For this, you have an indefinite data set, so you really can't figure out the variance for it. So you got mean, you have a sum of probabilities equals 1. Now, here is our notation. Remember, you want to start out with proper notation because it provides you with the information that's important. So here's our random variable x is distributed, this little squiggly mark, distributed now with a capital G, geometrically, and our parameter instead of NP is just P, the probability of success. Again, I like to put the Q off to the side because it's also important. If you know P, you automatically know or can figure out Q. Q is our probability of failure. So here is our formula now for the geometric for finding the probability that you will get a success on a particular trial. In other words, the Rth trial, whether the Rth is the 3rd one or the 30th one or the 300th one, the R represents which trial you're finding the probability of getting a success, meaning all the previous ones were failures. So obviously you have to have one success and all the rest, meaning your R minus the 1, all the previous ones are failures. So this is going to be our formula. This is our notation. And this is what we need to succeed in these question types. So let me set up for our first example. Okay, for our examples, because this is new material in the new syllabus, I don't have any past papers to draw from yet. And I did look at the specimen paper. There is a part of one question that could use the geometric, but there's actually an easier way to solve it. So I really don't find the specimen paper helpful for this particular new topic. So I'm going to use questions from the newer series, Cambridge series of books for the Statistics 1 book, since that's all I have to work with. So in this first question, it says that there are repeated trials and the probability of each trial is 0.66. Now, actually, I don't remember if it specifically gives us any kind of indicator concerning discrete or continuous, but we're just going to assume right now that it's discrete. And it says the probability of each trial, so this has to do with the probability is constant, is 0.66. The part of it not being fixed number of trials is sometimes the key word is going to be repeated trials. So instead of a certain number of trials, you keep repeating the trial until you get a success. That's the concept that you're looking for. And the key word, at least in the textbook, is repeated. We'll see what happens when it comes out in Cambridge test papers. So for this particular one, it says, find the probability that the first success is on the third trial, on or before the second trial, and after the third trial. So this is basically just straightforward using the formulas. Of course, because we're working with discrete data, you have to pay close attention to the inequality. So please, with binomial and geometric, you really need to focus on whether the equal sign is included or not. Write that in your notes. Pay attention to the inequalities. Okay. So first, of course, we want to do our notation. So our random variable is distributed geometrically. Our parameter is the probability of success, 0.66. And of course, I put off to the side failure, 0.34. So if the first success is on the third, here we write our probability statement, our probability that our big X equals 3 representing the little x, the trial that gets the success. So this is just going to come out with quite easy. Here's our formula. I rewrote some of the information over here so we had a little bit more room to work with. So here's the notation. Here's our formula. So the probability of it being on the third, there's going to be one success and R minus one failures. So we're going to get a 0.34 to the 3 minus 1, or in other words, 2. And when you multiply that out, 0.66 times 0.34 squared, you should get 0.0763. And you want to go again to 3 significant figures unless they tell you otherwise. And also, again, remember zeros on the left of your other digits are not significant. Zeros in between other digits are significant, and zeros to the right of other digits are only significant if the decimal is expressed. Okay, so that's our first one. Very simple, very easy, straightforward use of the formula. Now we get into the inequalities. So again, pay closer attention to the inequality part. If it is on or before the second, then that means that this is the same as the probability of X equaling 1 or 2. Okay. Now, with the binomial distribution, it was possible to have 0 as one of your little x's. 0 was a possible value in the binomial distribution. It is not a possible value in the geometric because the geometric is going based on the rth trial, the trial number. You can't have a 0 trial number. So you don't start with 0 with geometric. Generally with binomial, you do start with 0 because it is possible to have no items in that particular question type. So again, you need to have half of these problems as mental attention to details. Okay, so here is another way of stating this probability. Notice the 2 is included in the inequality, so we include it over here. Now it's just a matter of following the formula. So we have a 0.66 times a 0.34. For this first one, 1 minus 1 is 0, so to the 0 power, plus 0.66 times 0.34. 2 minus 1 is 1. And when you add up those two probabilities together, you should get 0.884. Again, I don't write zeros in front of the decimal. I've just seen it kind of as a waste of time. The decimal tells you the place value, where you're at in the place value. So if your teacher requires it, please write it in the front, but I don't write it. I don't know if it's a bad habit or just because that's the way I do it. Either way, just letting you know, I don't put zeros in front of decimals, generally speaking. So after the third trial, excuse me. So after the third trial, our probability that our random variable, which is the trial number, is greater than 3. After the third one does not include the 3, so we have greater than 3. This can, now, if you go greater than 3 on an indefinite distribution table, that means you have greater than 3 starts with 4, 5, 6, 60, 600, on. Obviously, we don't want to go in that direction, so we can restate this as not, which is our 1 minus the probability that x equals 1, 2, or 3. So if it occurs after the third, then that means it does not occur on the first, second, or third. So we calculate those 3, because it's a lot easier to calculate 3 than indefinite, and then subtract it from 1. As we saw in the concepts part, the total distribution probability equals 1. So 1 minus the naught is our value. So this is going to be 1 minus 0.66, that's 1 success, 0.34, no failure, plus 0.66, 0.34, 1 failure, plus 0.66, whoops, went the wrong way, 0.34, 2 failures, and this is going to give us our answer. And I don't have a lot of room down here, so I'm going to squeak it down here at the bottom. I guess you can see it. All of this equals 0.0393. So I hope you can see it there at the bottom. 0.0393 should be the answer to all of this. 1 minus the first one, 1 success, no failures. The second one, 1 success, 1 failure. The third one, 1 success, 2 failures. These 3 added up are the not greater than 3, and we subtract it from 1, and we get 0.0393. Again, 3 significant figures, 3 significant figures, 3 significant figures, and this is the basic way the formula works. Okay, now let me set up for the second example. Okay, here's the second example, and you're going to start seeing where the mental concept becomes a little bit more challenging than just simply plugging it into a formula. So this particular question says that 18% of people wear contact lenses. Now, right away, we can see that this is discrete because you're dealing with a number of people, and that's discrete data. And there's not a fixed number of trials. You just keep randomly selecting people from the public until you find the first one that's wearing contact lenses, okay? So the CL for contact lenses, you just keep selecting a person, interview them, see if they wear contact lenses. If not, you go on to the next one and on to the next one. And so there's not a fixed number of trials. So we're dealing with discrete data. A person either wears the contact lens or they don't. And we're dealing with continuing to select people until you find one that does wear contact lenses. So this is like repeated selection, or there's no fixed number of people that you're looking at. So not a fixed number of trials. So we set up our distribution here. Our random variable X is distributed geometrically with a probability of success is 0.18, meaning our probability of failure is 0.82. Now we get into this little bit of mental concept that we need to work on. And it says, find that your first person to wear contact lenses is any one of the first 15. So it's not asking you for the 15th one or even the first one. It's asking any one of the 15, means it could be on the first, could be on the second, all the way to could be on the 15th. So the probability that your random variable is less than or equal to 15. Now, if we use the formula for this, that means we have to go from 1 to 15. And technically, you should be able to do that. You should be able to add up the probability of x equaling 1, x equaling 2, x equaling 3, all the way up to x equaling 15, and add them up together. But there is an easier way of doing it. If we want to find out that there is a probability of success somewhere in the first 15, that means we can't have all failures 15 times, right? If there has to be a success somewhere in the first 15, then that means we cannot fail 15 times. So if we do 15 failures, that would represent the first 15, fail, all 15 times, and subtract it from one, that should represent all the probabilities of a possible success being anywhere between 1 and 15. So if we work on that one, we're going to get an answer of 0.949. 0.949 is our probability of the first one occurring within the first 15, which is a high rate of probability, almost 95% chance that you'll find someone who wears contact lenses within your first 15 people that you select randomly. So again, we didn't use the formula directly. You could have, but you would have had to add up 15 different values, which again takes time. So you want to work smarter, not harder. And so you can see that this requires that you can't fail 15 times. Now, as we move on to the second one, it says, find the first to wear contact lenses is not one of the first 9, not one of the first 9. So in this one, we see that our probability is that our X, that is the number of people that we're interviewing or trials, has to be greater than 9. We don't want the success in the first 9. We want our first success to be after the first 9. Well, this one would be really hard to do by formula because you would have to start with 10 and go indefinitely. So we don't want to do that. But another way you could put this is this means that if our first success is after 9, then that means we have to fail 9 times. If there's not a success in the first 9, that means we have to fail 9 times, and the success can be anywhere after that. So really all we have to do here is fail. Why did I put a P here? Sorry, that was supposed to be our Q. This is the P, that's the Q. So all we have to do is fail 9 times. And if we fail 9 times, we get 0.168. So there's a 0.168 chance that you will fail 9 times. That means somewhere after the 9, your success will come. So this one up here, I didn't really write the numbers in, but it would have been a 0.82, the failure to the 15th power equals the 0.949. Okay, so notice in both of these, we actually only used the failure. We didn't use the probability of success at all, except in the notation. It was the probability of failure. If your probability of success is before 15, then that means you can't fail 15 times. If your probability of success is after 9, that means you had to fail 9 times. So again, understanding the relationship between success and failure with respect to these inequalities is important. Again, after 9 means the 9 is included on the front side. Less than or equal to 15, again, means you had to fail or can't fail 15 times. So, excuse me, again, and let's look at one more example. Okay, here's our last problem, or at least the last example that the book gives to us. And again, you have to do a little bit of thinking here. It says you have, basically you're going to be tossing a coin, but this coin is biased, meaning it's not 50-50 heads and tails, doesn't have equal values. It's a biased coin where the probability of you getting a heads is 5/11, and you're going to flip the coin until you get the first head. So since, again, it's discrete, your outcomes are either, head or tail. You're flipping a coin. This is discrete data. You either get a head or you don't. You don't get half a head. And so it's discrete. And it's not a fixed number of coin tosses. You're going to continue to toss it until you get the head. So you're going until the first head shows up. So what is the probability that you flip the coin at least 6 times? And what is the probability that you flip the coin fewer than 8? So we set up our notation first. The probability that X is distributed geometrically. Our probability of success is 5/11, which means that our probability of failure is 6/11. So when we go to write the probability statement, it's important you write both of these. This one gives you the information you're working with. This one sets up the question as a probability statement. So the probability that your random variable, that is your number of coin tosses, is at least 6. That means 6 is the smallest and included, so it's greater than or equal to 6. Now, remember, this is going from 6 and larger, so it's going to go indefinitely. Obviously, we can't do an indefinite number of formulas, so we need to rethink this. So if this has to be greater than or equal to 6, that would be the same thing as your probability of X simply being greater than 5. Now, the reason why we want to do that is because the 6 is included in your starting point going on indefinitely. So since 6 is included on that side, when we look at the front side is going to be 1, 2, 3, 4, 5. Okay? So if our success has to be after 5, meaning it could be in 6 or 7 or 8 or 9, if it has to be after 5, then that means we cannot fail, means we have to fail. We have to fail at least 5 times. So our failure has to be 5 times, and then any time after the 5 failures, you can have a success. So q to the 5th power, we have at least 5 failures. So we have 6/11 to the 5th power, and that should come up to 0.0483. So in other words, there's just almost a 5% chance that you'll get ahead sometime after or including the 6th toss. Only a 5% chance, because you can only have 5 failures, and any time after the 5 failures, you will have your heads. Okay? Then fewer than 8 is going to be probability that x is less than the 8, meaning that we can restate this to being the probability that x is less than or equal to 7. Less than or equal to 7. If it's less than 8 and this is discrete, then it's less than or equal to 7. And if our probability that we have to have a success somewhere in those first 7, then that means we cannot fail 7 times, right? We can fail once all the way up to 6, but if it has to occur in the first 7, if it's fewer than 8, if it has to occur in the first 7, including the 7th, then that means we cannot fail 7 times. So 1 minus q to the 7th equals 1 minus 6/11 to the 7th power, and you calculate that, and you'll get 0.986. So there again is a little bit of mental play that you have to work with. Again, you could add up 1 through 7 and do the formula 7 times and add it up, and you'll still get 0.986. I haven't tried it, but I believe you will. That would take longer to do, a little bit of thinking. With the not failing 7 times is the faster way. Up here, you could not do this with the formula because it's going on indefinitely. So you really do need to think of what that means in terms of, well, you have to fail at least 5 times to be more than 5. So it's a little tricky. Again, this is a new distribution that they've added to the new syllabus. We'll see what it looks like when it comes out in the past papers. Maybe sometime in the future I'll, update the video, but this is what we got for now, and I hope that you're able to be successful. At least it gives you something to think about. As always, thank you for joining me, and I look forward to seeing you again next time.